All right, let's go ahead and try a problem using the chi-square. So we're going to kind of continue with this virus problem that I worked on previously. So just a little recap. Remember, you calculated the allele frequencies and the genotype frequencies based on some information given about a genotype which creates a situation where someone is more susceptible to the severe effects of the virus. Now remember, previously it was 39% of the population has that particular genotype. So we know that for sure. But now let's say we've determined that the actual observed data in terms of homozygous dominant, right? Those that are homozygous dominant is 11% of the population. And let's say we have a population of 1,000, makes the calculations a lot easier. So this is what's observed, right? So we know that 39% of the population, or 390 individuals, have the genotype. And now we've determined that 110 of those individuals that do not have that genotype are homozygous dominant. So if we subtract these two numbers from 1,000, we can get the heterozygotes. So that should be 500. Now, what was expected is we use these genotype frequencies that we calculated already, multiplied by 1,000. So what would be expected is 141 here, 469 here, and 390 here. Now what we want to do is determine whether this population is in Harding-Weinberg equilibrium. So what we need to do is calculate the chi-square, right? So we use the chi-square test in order to determine this. So chi-square is equal to the sum of these numbers right here. So if you take all three data sets and you're going to subtract the expected from the observed numbers, and then divide by the expected numbers, and these are squared here. Okay, so it's the sum of all of those three together. So let's go ahead and set that up. I've already calculated it. However, I'm going to show you how to set it up. So here, chi-square is going to equal 110 minus 141, and that would be squared, and then divide that by 141. And then you're going to add that to 500 minus 469 squared over 469 plus 390 minus 390 squared, which gives you 0 over 390, which is just basically going to cross out. Okay, so that's going to be 0 over a number, and that's not going to give you anything. So then you just basically calculate these out. So chi-square is going to equal 6.82 plus 2.08, which is equal to 8.90. Okay, so that's your chi-square number. Now what you want to do is determine your degrees of freedom. Okay, so remember the degrees of freedom which you read about in the lab manual. So since you should probably already know this, you have three data sets, and the degrees of freedom equals the number of data sets minus 1, so that's 2. Okay, so you're going to use this to look up in the table in your lab manual, the chi-square table. So you're going to look up using the row for degrees of freedom of 2, and then you're going to look for the number, where the number 8.90 would fall. So if you go across to 2, you're going to pass that p equals 0.05, and then you're going to end up with a number between p equals 0.02 and 0. So it's going to be somewhere in between p equals 0.02 and 0.01, right? So that is greater than the p equals 0.05, all right? So that means the null hypothesis is rejected. Okay, what that means is that, well, since the null hypothesis states that the population is in equilibrium, if we're